Continuing from here, let's look at other examples. So what have we finally said? We said that the limit of any polynomial as x approaches a, you end up substituting a. You tell me this is the case all the time? Yes. Polynomials are smooth functions. They don't have any problems. So their limit around a will always be p of a. Moreover, the limit as x approaches a, if I have not only a power, if I have a root. Remember we said we said in the previous session that the limit of f of x to the power n is nothing but the limit of f of x, all of it raised to the power n. Not only powers work, even roots work. So if I have the limit of this, what do? I get the limit of f of x, and then the answer, what do I do to the answer? I take its nth root. So for example, the limit as x approaches 2 of the fifth root of 3x squared minus 2x would be what? Would be the limit of 3x squared minus 2x as x approaches 2, and the answer, which is the fifth root of 3 times x squared, which is 2 squared. 2 squared is 12. 12 minus 4, 8. So it's the fifth root of 8. Look at another example. That's example number 3.5. And see here how when you think about things rationally, things should make sense to you. Limit as x approaches 0 of root x plus 2 minus root 2 over x, and we want to find it. Now, according to what we have learned, if we want to find such limits, then we end up substituting. Limit of a root is the root of the limit. What's the root of the limit at 0? The limit of x at 0 is 0 plus 2, 2 minus the limit of any constant is the constant itself over the limit of x as x approaches 0, 0. This is what? Root 2 minus root 2, 0 over 0. Problem failed. When we fail like this means that we started off in a wrong way. What do I mean by we started off in a wrong way? We are allowed to use quotient rules if the denominator is not 0. But when we substitute 0 here, we got the denominator is equal to 0. This doesn't mean that we cannot continue. It means that the basic substitution did not work. What do we need to do? We need to do more work for things to be okay. What kind of more work? Again, if you remember how our approach is, you should know what to do. Our approach is we substituted 0 in the upper part and we substituted 0 in the lower part. Both of them gave us 0. See, the trick here is the fact that we get 0 over 0. The trick is not the 0 in the denominator. The trick is that the 0 up and the 0 down are happening at the same time. When we have this scenario, this means that there is an x here hidden, an x factor, and here there's an x factor hidden. Now in the denominator, I'm lucky I can see it. In the numerator, it's hiding somewhere. Why x? Why I didn't look for x minus 1 or x minus 2? Because we said when we substitute x equals 0, this means what is the factor we are looking for? X minus 0. And what is x minus 0? X. Whereas here, for example, in the question where we did the factoring, what were we substituting? X approaches 1. This gives me the 0. This means the factor is x minus 1. That's why we search for x minus 1 up and down. So over here, we were searching for x above and below. See, in problem before, we factored because we had polynomials. Here, I want to find an x in this, but this, the way it is already, I cannot see the x alone as a factor on its own. And I cannot factor roots. So I start thinking how to change the shape of those roots. See, one way of changing the shape of this that we have learned from before is what we call to rationalize, or multiplying by the conjugate. What is the conjugate of root x plus 2 minus 2 minus root 2? Conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. Those are conjugates, all right? They are not inverses, they are not opposites, they are conjugates of each other. So over here, if this is a minus b, then the conjugate is a plus b. But if I multiply by a plus b on top, I would be changing the equation. So what I do is I also multiply by it in the bottom. So what does this give us? The conjugate this times that. Why do I use conjugates? I don't use something else. I use conjugates because of their beauty. What is the beauty of conjugates? When I multiply a minus b by a plus b, the answer is, this is the opposite of the difference of two squares. Yeah? So when I expand it, it gives me a squared minus b squared. A times a plus a times b minus b times a, which cancel each other, minus b squared. So what we are left with is a squared minus b squared, which nicely, when I have roots, changes things into better ways, or different ways, not necessarily better, different. So root x plus 2 is a minus b, and here I have a plus b. The result will be a squared, so root x plus 2 squared minus b squared over the denominator. I will keep it exactly the same because I don't need to mess with the denominator. In the denominator, I need to find a factor of x. I already have it, so why do I need to really change anything? I don't really need that. So now what happens is I want to simplify. Now this becomes limit root x plus 2 squared. The root and the squared cancel each other. I'm left with x plus 2 minus the root 2 squared. The root 2 cancelled, so squared, you get 2 over x stays the same in the denominator, root x plus 2 plus 2. Now simplifying, x plus 2 minus 2, the answer is nothing but x. Do you see how by rationalizing or by multiplying by the conjugate, we have changed the shape of our function? We changed it. This that we started with and this, they are equivalent functions, but they have a different shape. They are equivalent functions, but with different, they are hiding. Just like, for example, if I tell you root 2 and 2 over root 2. So just for you as a reminder, root 2 is the same as 2 over root 2. Right? They are exactly the same, written in a different way. Similarly, 1 over root 2 is the same as root 2 over 2, but written in a different way. We look at them, we see they are different, but aren't they exactly the same? Yes. What do we do in order to change them? We multiply by the root 2 up and down and so on, so this is exactly the same as what we have done over here. We started with this function, we multiplied by the conjugate up and down, we simplified that multiplication, we got this result in the end. I know I'm on the right track because I was searching for a factor of x up and down. I found it. And when I find the same factor up and down, what can I do? I can cancel it. I can only cancel x with x if x is not 0. But what guarantees that x is not 0 for me? The limit. When I'm doing limits around 0, this means I'm looking at the neighbors of 0, but I'm not looking at 0. So because this is the case, I cancel the x with the x. What do I have left? The limit as x approaches 0. X cancelled with x gives me 1. It doesn't mean this becomes alone. It's a common mistake. Students cancel the x with the x. What do they think we have left? Limit root x plus 2 plus, sorry, I copied wrong, root 2. Yeah? No, when you cancel the x and the x, what do we have left up? 1 over root x plus 2 plus root 2, which is equal to, now I can do the limit again algebraically. What's the limit of 1? 1. What's the limit at 0 of root x plus 2? It's the root of the limit of x plus 2, which is 0 plus 2, 2, plus the limit of root 2. Root 2 is a constant. This gives me 1 over 2 root 2. Or another way of writing this in a rationalized way is root 2 over 4. Whichever way, of course, you prefer to write it. Whether you use this way or you use the calculator will always give you the rationalized form, will never keep a root in the denominator. But in all cases, for me, personally, both answers are totally correct. Now, for other functions, we have only discussed here, if you noticed, polynomials or powers and so on. For other functions, what about other functions? See, for other functions, first, like sine x, cosine x, and so on, so like, the limit of sine x as x approaches a is the same as sine a. Because if you look at this, this is the sine function, and so on. If you choose any a, do you notice the function has no problems? So f at a is here, and the neighbors, all their x values, what are they approaching? They are approaching the same limit, which is f at a. Here, if you choose this number, b, this is f at b. And the neighbors, what are their images? These are the images. As we approach b, the images are approaching this value. And as we approach b from the right, the images are also approaching the same value. So the limit of sine x as x approaches a is sine a again. We again come back to the idea of substitution. When things work, substitution is our deal. Then the neighbors and the function itself and the center will be working exactly hand by hand. Limit cosine x at x approaches a is cosine a. Limit ex as x approaches a is ea. Again, just for you to remember, ex looks like this. Yeah, so this is at 0, it's 1. If you take any a, this is f at a, or e to the power a. As we approach a from the left and the right, what will the images of those neighbors approach? Again, they will be approaching this number, so they are approaching e to the a. The same happens for ln x. As x approaches a, the limit of ln x is a. But careful, this only works when a is positive. Why when a is positive only? Because logarithms are only defined for positive values. If you remember this, how logarithms look like. This is the function y equal ln x, and it's very important to memorize the shapes of those functions. See, if you take any a value, since as you notice the function does not have any problems, then this will be ln a. And as I approach a from the left and the right, imagine here there are points approaching a. Then their images here, let's check what the pattern of the images. Those are the images. What's happening to the images as I come closer and closer to a? As I come closer and closer to a, the images are coming closer and closer to the number ln a. Similarly, if I look at the right neighbors and their images are here. As I come closer to a, the images are coming closer to what? They are coming closer to this point, which is ln a. But all of this can work only if a is in the domain of the logarithm. What's the domain of ln x? The domain of ln x is from 0 to plus infinity, where 0 also is not included. You notice we cannot define len 0. We only define len for values strictly greater than 0. Moreover, sine inverse x, again, the limit of sine inverse x around a is a. The limit of cosine inverse x around a is a. But here you have to be very careful. The a that you're working with should be between -1 and 1, because if you remember, sine inverse and cosine inverse, they are only defined from -1 to 1. Why is that the case? Because if you remember, sine inverse is the inverse function of sine. Sine x, the domain is all real numbers. It's defined for all real numbers. But what is the range of sine x? The range of sine x is from -1 to 1. When we get inverse functions, the inverse function of sine x will have the domain equivalent to the range of the sine x. So sine inverse x, those will exchange. So the domain of sine inverse x is from -1 to 1, and the range of sine inverse x is all real numbers. That's why here it's very important to realize how things are. Okay, so the range is from -1 to 1. It's only defined from -1 to 1. 7, tan inverse x is tan inverse a for all real numbers. A can be from -infinity to infinity. We don't have any problems. And the last thing is composition. If we have x approaches P of A is L, then limit as x approaches A of f of P of x is L. What does this mean? This looks complicated, but here it's not that complicated. This means that if we have composition of two functions with each other, so let me tell you, if I have limit sine inverse of x plus 1 over 2 as x approaches 0. How will I do that? This is not sine inverse x alone. All right, and it's not a rational function or a polynomial alone. It's sine inverse composed with x plus 1. So this is a function of a function. What do I do in order to get the answer for this? I will take the 0 and I will get the limit of this. What's the limit of the inside function at 0? It is limit. What's the limit of this at 0? It's 0 plus 1, 1 over 2. So as if I'm getting the limit of sine inverse u, but now what is u approaching? 1 over 2. So it's as if we have sine inverse of half. You do 2 layers. It's exactly the same as when you are trying to find the value. How do you find sine inverse x plus 1 over 2? Let's suppose this is your function. How do you find f of 0? Normal composition. You plug 0 in this one first, and the answer will be half. Then you apply sine inverse on the answer. So sine inverse of half. What is sine inverse of half? Sine inverse of half is pi over 6, 30. All right, the same happens here. In order to get the limit of a composition of two functions, then you get the limit of the inside function at this, call this one u, and now the answer becomes your new limit, and so on. So you substitute one in terms of inside of the each of the other, one inside the other, till you are done. One of the very important theorems in this section is called the squeeze theorem. All right, so we are learning different techniques to find limits algebraically. See, sometimes functions, I cannot tell what their limits are. So let me tell you an example of that. Limit as x approaches 0 of x squared cosine 1 over x multiplied by each other. Now, if I want to use the properties I have learned so far, this will be the limit of x squared alone, which is fine, times the limit of cosine 1 over x alone. This is how it is, right? This is how it is. This, no problem. What's the limit of x squared as x approaches 0? 0. But now when it comes to this is a composite function. It's cosine of 1 over x. You need to put 0 in 1 over x. And then the answer, you put it inside of what? Cosine. Remember, just as we did over here, you have to start from the inside to the outside. What is the limit of 1 over x as x approaches 0? As x approaches 0, 1 over x blows out of proportion, goes to infinity. You tell me, yeah, and what's cosine infinity? See, cosine is a function that oscillates. So as the function goes to infinity, cosine does not have any answer to what the limit is. So as x goes to 0, 1 over x will blow either to plus infinity or to minus infinity. And cosine 1 over x is oscillating back and forth between minus 1 and 1. So does it really have the limit? No. So can I find this limit on its own? No. And because I cannot find it, many students would say 0 times anything is 0. No, not really. 0 times anything is not 0. 0 times a number I know is 0. This is not a number I know. This is a quantity that is unknown. I do not know what it is. It's a quantity that does not exist. How will I multiply 0 by a quantity that does not exist and say that the answer is 0? It doesn't work. So you tell me, what do? I will come and I will ask the squeeze theorem for help. What does the squeeze theorem say? The squeeze theorem, I like to call it sometimes the sandwich theorem because it allows me to explain it better. What does the sandwich theorem say? The sandwich theorem says that if you have a function and you can bound this function between two other functions, so you have a function g and you bind that function between f and h. What does that mean? It means you are able to find a function that is smaller than g of x and another function that is bigger than g of x, call it h of x, for all x that we want in the domain that we are working with. If you can do that, then this function is between them, right? Between f and h. The squeeze theorem says if the limit at a number a of f is equal to the limit at a of h to a finite number L. So if this upper function and this lower function have the same limit at a, what does it mean they have the same limit at a? يعني around a, they behave exactly the same. طب I have a sandwich. I have one bun and the upper bun and I have the filling in between. If the upper bun and the lower bun meet at one place, if the upper bun and the lower bun, they meet at one place, they become exactly the same at one place, what will happen to the filling inside? It will be exactly the same. It cannot escape. See, let me show you the example. You have the function in black, g of x, in between f and h. If f and h around a, they meet at exactly the same limit. They happen to behave exactly the same way. Where will the filling go? The filling is above f less than h. It's between them. And they are already equal to each other. What is between two equal numbers? The same exact number. So if the limit of the upper is equal to the limit of the lower, then the filling, without really testing it, will have the same limit L. Tell me now, how does this help me to solve problems like limit x squared times cosine 1 over x as x approaches 0? See, with the beauty about cosine and sine functions is that they are always bounded by -1 and 1. No matter what they oscillate, which we're saying it oscillates, so I cannot control its movement. Yes, it oscillates and I cannot control its movement, but I know it has to move between -1 and 1. This is this function. I want to study all of this package. So I need to change this initial condition. I need to change it into this package over here. To change it into this package over here, what do I have to do? I have to multiply by x squared the whole equation. Can I multiply by x squared? When I'm working with inequalities, there is a beautiful thing that when you multiply by a positive number, the inequality does not change. So am I allowed to multiply by x squared the whole inequality? Yes, since x squared is a positive number. So this becomes minus x squared less than cosine squared, x squared cosine 1 over x less than 1 times x squared, which is x squared. Now I have bounded this function between a lower bound and an upper bound. My duty now, I do not study this limit. This limit I should deduce according to the sandwich theorem. When I'm able to sandwich a filling between upper and lower bounds, I only study the limit of the bounds at the same digit here. The limit of the lower bound minus x squared at 0 is what? It's minus 0 squared, so it is 0. The limit of the upper bound x squared, the limit of the upper bound around 0 is 0 squared, which is also 0. Is the limit of the upper bound equal to the limit of the lower bound? Yes, since they are equal to each other, then the limit of the filling, what is the filling? It's the one in between, which is what we want, has to be exactly the same by what we call the squeeze theorem or the sandwich theorem. This is the technique of the squeeze theorem or the sandwich theorem. We cannot tell anything about this weird oscillating function, but what I can tell is that because cosine 1 over x is between minus 1 and 1, then x squared times cosine 1 over x is between minus x squared and x squared. And because this is the case, because it's between minus x squared and x squared, and I know that the limit of minus x squared is equal to the limit of x squared is equal to 0, then the limit of the filling in between is also equal to 0. All right. One more idea before we move on to a new section. All right, let's look at example 3.9, which is limits of piecewise functions. What do I mean by piecewise functions? I mean functions that are given in pieces relative to different domains. So this means when x is less than 0, f of x is equal to x squared plus 2x plus 1. When x is greater than or equal to 0, f of x is equal to ex minus 4. How do I apply piecewise functions? For example, if I ask you what is f at minus 2, what do you do to answer this question? You ask, is minus 2 less than 0 or greater than 0? To know which piece do you use. Minus 2 is less than 0, so which piece do you use? The upper piece. This is minus 2 squared plus 2 cosine minus 2 plus 1, and you find the answer. If I asked you what is f of 3, what would you do? If I asked you what's f of 3, the first thing you do is you check which of the pieces is 3 belonging to. 3 is greater than 0, so it belongs to this branch. So I use this branch for substitution, and you get the answer as well. And this allows me now to, this is talking about pure substitution. What if I wanted to find the limit around 0 of f of x? See, the first thing I have to ask myself, what does it mean to be studying the limit around 0? It means I want the neighbors of 0. Okay. Now I need to know whether I need to substitute in this function or in this function. To answer whether to substitute in this or that, I need to know whether 0 is here in this domain or here. See, 0 in particular has two neighbors, the right one and the left one. The left neighbors of 0 are less than 0, and they belong here. The right neighbors of 0 are greater than 0, so they belong here. This means this cannot be done at one shot. I have to do the limit at 0 minus alone and the limit at 0 plus alone, because 0 in this particular example is called the separation point. It's the point that separates the two pieces from each other, the two branches from each other. Branches and pieces came together into pieces. So over here, f of x equals limit as x approaches 0 minus. What does x approaches 0 minus mean? It means that x is less than 0. When x is less than 0, what is the function that we use? And thus now I substitute 0. I get 0 plus 2 cosine 0 plus 1. 0 plus 2 plus 1, 3. Now for x approaches 0 plus, it means x is greater than 0. We are approaching 0 but greater than 0. If we are greater than 0, then what branch should we use? ex minus 4. So this gives me e to the power 0 minus 4, which is 1 minus 4. The answer is minus 3. Is the left limit equal to the right limit? No. This means what is this limit that we were looking for? We were looking for the limit around 0 of f of x. This will be does not exist because the limit from the left is not equal to the limit from the right. All right? Makes sense? So this is basically section 1.3. There are a lot of problems and I want you to solve those problems, because if you do not solve them, then you will be you will not be ready, because if you do not solve limits, you will never be ready. Even if you have done this course 10 times, if you are not solving, then you are not ready. So please make sure that you solve every single example in the limits section in order to be ready to solve problems like these. So we will do some together. So now we move to exercises because we are done with the examples. So there are examples where you just need to substitute, and substitution will not cause any problems. So x squared minus 3x plus 1 equal. According to algebraic rules, the limit of this is 0 squared minus 3 times 0 plus 1. So 0 minus 0 plus 1. That's great. I don't have any problems. The answer is 1. And we're done. Similarly, limit as x approaches 2 of cube root of 2x plus 1. This is equal to cube root of the limit of the inside. What's the limit of 2x plus 1? It's 2 times the limit of x, which is 2, plus the limit of 1, which is 1. 2 times 2, 4, plus 1, 5. So the answer is cube root of 5. So some examples are very simple and very straightforward. The limit as x approaches 0 of cosine inverse x squared. Again, this is an example of a composite function. We do the inside, of course, first. So this gives me limit of cosine inverse u as u approaches. What happens when x approaches 0? What happens to x squared? It approaches 0 as well. So I hide it, I call it u, and now what does u approach? Approaches 0. What's now cosine inverse of 0? Cosine inverse of 0 is pi over 2. Always your answers should be in radians, not in degrees, so make sure your calculator is in radian mode. Sometimes students mistake things. They assume there is a problem and they start solving before they check that there is a problem. First, we do substitution. We never assume we should do extra work before we really need it. So here, many students start factoring and canceling and make problems. Not really. What do we have to do first? Limit of the upper is 2 minus 5. The limit of the lower is 2 squared plus 4. 2 minus 5 is minus 3. 2 squared 4 plus 4, 8. Perfect. Nothing to do. Nothing extra that we should worry about. 5. Limit as x approaches 3 of x squared minus x minus 6 over x minus 3. Again, our first stage is substitution. So we do the upper first and the lower alone. 3 squared, 9, minus 3 minus 6 over 3 minus 3. We don't do it on the calculator one shot because it will give us math error, which means many students assume it means it does not exist to become low. It's not the case. You have to do the upper and the bottom one alone. 9 minus 3, 6 minus 6, 0 over 3 minus 3, 0. This is what worries me. There's a 0 in the denominator. When there is a 0 in the denominator, I need to pause and check my problem. See, when I pause and I check my problem, I see there's another 0 in the numerator. See, when I see a 0 over 0, this means that when I substituted 3 in the upper term, it caused 0. This means, what do I have hiding upstairs? I have a factor of x minus 3 hiding upstairs, and I have a factor of x minus 3 hiding downstairs. Those are your thoughts. So for anyone who is reading my notes, this is me thinking. Because I got 0 over 0, when I substituted 3, this means that x minus 3 is a factor up and it's a factor down. My duty is to find that factor. Obviously, this is a problem where factoring will help me find the factor. How to factor x squared minus x minus 6? Two numbers, their product is minus 6, their sum is minus 1. It's x minus 3, x plus 2. The x minus 3 in the denominator is already there and ready. We do not need to worry about it. See, when I factor and I find this x minus 3 and x minus 3, I know I can cancel them. Why do I know I can cancel them? Because I can cancel terms that do not cause a 0. X minus 3 does not cause a 0 when x is not 3. So that's perfect for me. So when I cancel, what do I have left only for me? The limit as x approaches 3 of x plus 2, which is equal to the limit of x 3 plus 2. Together they get a 5. This is if we want to work in a very neat and organized manner. Limit as x approaches 1 of x squared plus x minus 2 over x squared minus 3x plus 2. Again, I try first if things can work without a mess. To check if things are working without mess, I just need to use the algebraic properties. The limit of this is the limit of the upper, so 1 squared plus 1, 2 minus 2, 0 over 1 squared 1 minus 3 minus 2 plus 2, 0. The moment I see this is the moment I need to have another look and do more work to see if things can be fixed. What is the more work? When I substituted 1 and up and down, I got 0 over 0. This means there is a term of x minus 1 hiding up and down. I just need to find it. I need to uncover it. To uncover it here, obviously here we have polynomials, so it seems very nice to factor. Two numbers, their product is minus 2, their sum is 1, plus 2 minus 1. Product is 2, their sum is minus 3, minus 2, and minus 1. I know this is the same term, exactly what I've been searching for. Can I cancel it? Yes. Why can I cancel it? Because I'm working with values that are approaching 1, but they are not 1. So what do we have left? I have x plus 2 over x minus 2. I find the limit. Limit of x plus 2 around 1 is 1 plus 2. The limit of x minus 2 around 1 is 1 minus 2. So this is 3 over negative 1. The answer is negative 3. Another example. So this was number 6, now number 7. The more examples you solve, the better you are. So limit as x approaches 2, x squared minus x minus 2 over x squared minus 4. Again, when I substitute 2, I get 4 minus 2 minus 2, 0. 2 squared 4 minus 4, 0. See the 0 over 0? What does that directly mean? I go and I write what am I searching for? What am I searching for? x minus 2. What is the method that will help me find what I'm searching for? Factoring, because I have polynomials. How to factor this? Very easy. Two numbers product is minus 2, their sum is minus 1. The answer is minus 2 plus 1. What is the factoring of x squared minus 4? This is a difference of two squares. It's x minus 2 into x plus 2. Again, since I'm working around 2, this means I'm not equal to 2. This means this is not 0. I can cancel them with each other. I'm left with x plus 1 over x plus 2. Now I substitute again. 2 plus 1, 3 over 2 plus 2, 4. And I found the limit that I'm looking for. Another example. Let's look at number 8. Limit as x approaches 1 of x cubed minus 1 over x squared plus 2x minus 3. This now over here, again, the first step is always checking whether we need to do more work or not. Sometimes we just need to substitute. 1 cubed 1 minus 1, 0 over 1 plus 2, 3 minus 3, 0. The moment I see 0 over 0, what do I know I'm looking for? I'm looking for x minus 1. Now, let me give you a reminder. Just as we have difference of two squares, a squared minus b squared, what is the factor of a squared minus b squared? A minus b into a plus b. A squared plus b squared can never be factored. We say it's prime, cannot be factored, as it's never equal to 0. A squared plus b squared يعني مثل x squared plus 4, a squared plus 1. Many students factor this. It cannot be factored. Please remember that. Factoring also of a difference of two cubes. You can factor a minus b cubed as a minus b, a squared plus ab plus b squared. And you can factor a sum of two cubes as a plus b, a squared minus ab plus b squared. So for example here, x cubed minus 1 is the same as x cubed minus 1 cubed, because 1 can be written as 1 squared, 1 cubed, 1 to the power 4. So here it seems reasonable to write it as 1 cubed. Then it will look exactly like this, with a equal x and b equal 1. So it's x minus 1, the square of the first, the product of the first by the second, and 1. All right, over here, this cannot be factored more. So when you do this cannot be factored more. If it can be factored more, this means that you have done something wrong. It's always the last one here is a prime factor. So over here, x minus 1, x squared plus x plus 1 over quadratic equation, two numbers, their product minus 3, their sum is 2, is x plus 3 into x minus 1. Do you see this is what I was looking for? An x minus 1 up and down. I found them. This means now my simplified form of my function for all values not equal to 1 is this. Now what's the limit of this? The limit of x squared is 1 squared plus 1 over the limit of x is 1 plus 3. So it's 3 over 4. Let's look at number 9. Limit as x approaches 0 of sine x over tan x. All right. Substitution. Sine 0, 0. Tan 0, 0. Whoa. 0 over 0. I need to do more work because 0 over 0 is an undefined quantity. So I need to do more work. I need to figure it out. So in order to do that, I need to try to cancel what's causing the 0 up and down. What's causing the 0 up? Sine x. What's causing the 0 in tan x? Sine x as well, but sine x that is hidden, so I need to reveal it. This is sine x over cosine x, which is rewritten in a simplified manner. It's cosine x over sine x. See, this sine x and this sine x cancel each other. What do we have left? Cosine x. What's the limit of cosine x around 0? It's equal to cosine 0, which is 1. Please remember now, there is a limit we studied in section 1.2. It's the limit of sine x over x as x approaches 0. If you remember, we did it using the graph. We did it also using numerical tables. And we showed that this limit is equal to 1. Also, if you take the reciprocal of that, the limit will also be 1. These two limits are very important. So please make sure that you remember them throughout. I do not like the form limit sine x over x as x approaches 0 because it makes things look narrower than they are. I like more the form limit sine theta over theta as theta approaches 0, which is limit theta over sine theta as theta approaches 0 is equal to 1. Why do I prefer this form? Because usually students, when you say sine x over x, they think this is the only form. No, even if I had something that looks like this, yeah, the first thing, this x approaching 2, not 0, yet this limit is the same as this. Why? Because what's the angle here? The angle is x squared minus 4. For me to use this formula, the sine, this angle, which is theta, should be the same as this, which is what also? Theta. Which is also theta. So they are exactly the same. So the first thing is that this and this should be exactly the same. The second thing is that when you substitute x to be 2, all of this package should turn out to be 0. Is it the case? Yes, because when I substitute 2 here, I get x squared minus 4. When I substitute 2, I get 2 squared 4 minus 4. The answer is 0. So this is sine a package over exactly the same package. And what's happening to the package? It's approaching 0. So this as a final answer is equal to 1. This is a very important thing, and this helps you in a lot of problems. So please make sure that you remember this throughout the case. I will be doing more examples for the next session. You try to do the examples on your own, and then later on you can check if the answers is correct in the session after.